Hi, good morning, everyone. Today we continue with the second lecture. First we recall what we introduced in the last lecture. In the last lecture, we introduced what is a Markov chain. So a Markov chain is characterized by the transition matrix P. And this transition matrix characterizes the conditional probability to jumping from one state to another state. And in the first lecture, we also introduced the two notions. The first one is called irreducible. So a transition matrix P is irreducible if for any xy, there always exists an integer number n such that Pnxy is positive. So this tells us there is a strictly positive chance to jumping from x to y in n steps. The second notion is called aperiodic. So a Markov chain is aperiodic. It means that the period of all the states equals 1. And in the last lecture, we also proved that if the Markov chain is aperiodic, then in fact we can find a universal number R such that Pnxy is positive for all x, all y, and any n greater than R. So this is what we proved in the last theorem of lecture 1. And in the last lecture, we also introduced what is a stationary distribution. So a stationary distribution pi, first, it has to be a probability measure. So this means it has total mass 1. And the second, it satisfies this relation. Pi times p equals pi. And in the last lecture, we also see that if this measure pi satisfies this relation, we know that if we start with pi, then the marginal law of any time is always pi. So this is why this measure is interesting. And today we have 4 topics. First, we will show that when the Markov chain is irreducible, there exists a unique stationary distribution. So first, construct one, and then show it is unique. And the second part is we talk about ergodic theorem. So this ergodic theorem tells us the Markov chain will finally converge to the stationary distribution in the sense of space average. And then we introduce another notion that the Markov chain will converge to the stationary distribution. It's called Convergence Theorem. The Convergence Theorem tells us the marginal law of xn will converge to the stationary distribution in a stronger sense. This stronger sense is under the sense of total variation distance. So this is a distance between two probability measures. So this is the plan of today's lecture. So now we start with existence of stationary distribution. So in the construction of a stationary distribution, we need to introduce 2 times. So for any state x, we define 2 times. The first is defined in this way. So this is tau x. And another one is called tau x plus. So here we see from the definition that tau x is defined for n greater than 0, and tau x plus is defined for n greater than 1. This is the only difference. And then let us see what's the difference of these 2 times. Suppose our Markov chain x0 starts from some vertex y, but this y is not x. Then in this case, we know that these 2 times are the same, because we know that tau x0 can't be the first one. N can't be 0, so n has to be greater than 1. So in this case, these two times are exactly the same time. The only case that these two times they are different is in the case that we start from x. So if the Markov chain starts from x, under this definition, our tau x will become 0, but tau x plus is always greater than 1. So this is the only case that they are different. And in this definition, we call the first one is the heating time. And the second one is called the first return time. Because the second one tells us we start from x, and this is the first time that we come back to x. So it is the first return time. And this is the only case that these two times are different. Okay, so first lemma, we will show that when P is irreducible, we always have the expectation of first return time is finite. This is an important ingredient in the construction of stationary distribution. So this is why we first proved this lemma and then constructed stationary distribution. Another remark is this property is important. Okay, remark. So this lemma tells us the expectation of the first return time is always finite. And this is true. This is always true when the state space is finite. So we will prove this lemma, and you will see that this is always true for finite state space. But this is not always true when the state space is infinite. And we will see in the fourth lecture that, in fact, when the state space becomes infinite, this is finite or infinite. Give us two scenarios for the Markov chain. One is called positive recurrent, and another one is called null recurrent. So when the state space is infinite, this is not always true. And in fact, whether it is finite or infinite will give us two completely different behavior of the Markov chain. Okay, today we just first prove that this is always true when the state space is finite. Okay, so proof. Since P is irreducible, we know that for any vertex xy, there exists an integer n. And this n depends on xy such that P and xy, jumping from x to y, is strictly positive. And now we define a universal small quantity epsilon. So it is the minimum one of this probability. And since our state space is finite, the quantity here is finite and everyone is strictly positive. So this epsilon is strictly positive. And we define R is the max of all possible n. And again, because of a state space is finite, the max of all its numbers is also finite. And then from these two quantity, what we can conclude is, so no matter given what happens for the Markov chain up to time n, the conditional probability from the definition of these two quantities, we can conclude that given the first part of the Markov chain, and then we consider what happens in time between time n and n plus r, the conditional probability that we hit y at some time between these two times is at least epsilon, because we know that there exists an integer number between these two numbers such that so there exists a number m between these two numbers such that Pn x and y is greater than epsilon. So this tells us the probability of hitting a state y between time n and n plus r is at least epsilon. So this is just from the definition of epsilon r. Okay, so from this observation, we can calculate what's the probability of tau y plus is greater than r. So this means our Markov chain starts from x, and from time 0 to time r, we never hit y. And because of the observation here, we know that this probability is less than 1 minus epsilon. Okay, so this is the probability for tau y plus greater than r. For any integer k, let us check what's the probability that tau y plus is greater than k plus 1 times r. So in this case, suppose we know what happens to the Markov chain up to time kr. So suppose first we know what happens to the Markov chain up to time kr, and then what is the probability we want to calculate here? So the probability means tau y plus is greater than and k plus 1r. We never hit y. And from the observation here, we know that no matter what happens before time n, so in this time interval, we never hit r. The probability is at most 1 minus epsilon. So first, suppose we know what happens after time kr, then the conditional probability of this event is less than 1 minus epsilon. And from this event, we can already see that tau y plus is greater than kr. So what we have is this probability is less than Okay, so we know that the probability for tau y plus is greater than k plus 1r is bounded by 1 minus epsilon times the probability when it is greater than kr. So we repeat the same procedure. We know that, in fact, we can conclude this probability is bounded by 1 minus epsilon to the power k. Okay, so then this quantity is pretty close to the expectation of tau y plus, because we just recall a fact is if n is a random variable taking value in non-negative integer numbers, then the expectation of this random variable, big N, has another way to calculate it. So it is the summation for n greater than 0, so to calculate the probability for big N greater than n. So this is a general fact for non-negative random variables. And now we want to calculate the expectation of tau y plus. So of course, tau y plus is a random variable taking value in non-negative integers. So we know that this expectation equals And we know what happens when tau I plus is greater than kr. And here we need the probability when tau I plus is greater than n. So in fact, they are not so different, because for n between kr and k plus 1r, we can always bound the probability of this event by the probability that tau I plus is greater than kr. And there are r of them. Less than. So it can always bounded by this quantity. And for this probability, we know that it decays exponentially fast. So this summation is finite. And this proves that the expectation of tau I plus is always finite. Okay, so this is the proof of lemma. For finite state space, we always have that the expectation of tau I plus is finite. And then we can construct our stationary distribution. Okay, so proof theorem. There exists a stationary distribution when P is irreducible. So now we just need to construct one stationary distribution. So fix a vertex in the state space Z. We define a measure pi tilde. So this pi tilde is defined in this way for any vertex x. Our Markov chain starts from Z, and we observe what happens before the first return time to Z. And we want to calculate what's the expectation of the number of visits to a vertex X. So in this way, we define a measure. But first of all, we don't know whether it is a probability measure. So because we don't know whether the total mass of this measure is 1. Okay, so for this measure, the first claim is this measure is stationary, so pi tilde times p equals pi. So after we prove this is true, we know that if we can check what's the total mass of pi tilde, then pi tilde normalized by the total mass will give us a probability measure. And for this probability measure, it is also stationary because it just corresponds to we divide constant to both sides. So for that normalized measure, it still satisfies pi times p equals pi. And then it will give us a stationary distribution. So first we prove this claim. Why pi tilde times p equals pi tilde? Pi tilde px by definition this is the definition of pi tilde times p. And then we plug in the definition of pi tilde. Here, just a few words. So for this expression, we are calculating the expectation of the visits to a vertex x. We have another way to write this expectation. So suppose we just put an indicator number. So the number of visits to a vertex x before time tau z is just the summation of is just this infinite summation. And the event here is xn equals x and n before tau z plus. And now we just put this summation outside the expectation. We will get the summation for pz. The event is xn equals visits x and n is before tau z plus. So this is just another expression of this definition. And now we plug in the definition of this pi tilde. So what we have is y. Okay, so here just the definition of pi tilde. And now let us observe what's the product of these two. So the first event is it is xn equals y, the n before tau z plus. So this event just means from time 0 to n, we never hit z. So it's just an event measurable with respect to the random variable up to time n. And this is just what happens to time n. And then we multiply this jumping probability. This jumping probability is always the probability that we jump from y to x within one step. So in fact, this product is exactly the probability that xn equals y and xn plus 1 equals x. So we jump from y to x within one step. And this event just measurable with respect to what happens before time n. So there's no effect to calculate this conditional probability. Okay, and then we switch the order of these two summations. We are summing over y, and what happens to y is xn equals y, and we summing over all possible y. So then this event just disappeared because we are summing over all possibility of y. So this is what we have for pi tilde times p. And here, n less than tau z plus, we can write it in the way that n plus 1 is less or equal than tau z plus. So there's no difference because all of them are integers. And now we are summing from n starting from 0 to infinity. So now if we replace n by n plus 1, it's just the summing for n greater than 1. So I've done nothing, everything is identical. So now what we have is pi tilde times p at x equals n greater than 1 So we just show that pi tilde times p equals this one. And from the definition of pi tilde, this is the definition of pi tilde. And here we can see that they are very similar. The only difference is here is n less or equal than tau z plus. Here is strictly less. And here is starting from n plus 1, n equals 1, but here is starting from n equals 0. And we want to show that these two quantities are equal. And here we can see that because the only difference between these two events is whether or not tau z plus equals n. And what happened? What's this mean for tau z plus equals n? Tau z plus equals n means we first return to z at time n. So this implies xn has to be z. But we also have an event that xn equals x. So if x is distinct from z, then tau z plus can't be n. And then these two events will be the same. So now here we see that we have to divide into different cases. So first, if x is not z, then we know that pi tilde px equals this quantity because tau z plus can't be n, so it has to be strictly greater than n. And also when n equals 0, x0 equals x, but we know that x0 is z. So if x is not z, when n equals 0, this probability is 0. So it's the same that we are summing starting from n equals 1. So this is exactly the second quantity. Here. So when x is not z, they're exactly the same thing. Okay, and when x equals z, let us check what's these two quantities. So pi tilde z. So pi tilde z, this is the definition of pi. This is what we have from that quantity. And now xn equals z. Tau z plus is greater than n, greater or equal than n. So now we know that tau z plus has to equals n because we already know that when at time n we're coming back to z. So here has to be equal. And when tau z plus equals n, we know that this implies xn equals z. So now we can remove this event. So now what we have is we're just summing for all positive, all n greater than 1 for the probability that tau z plus equals n. And this just all the possibility for tau z plus. So this equals 1. And what about pi tilde z? So pi tilde z. Okay, so this is pi tilde z. And here we already know that if this n is strictly greater than 1, this is impossible because xn is already z, and your tau z plus can't be strictly greater than n. So when n is greater than 1, this event is impossible, so the probability is 0. And the only possible event is for n equals 0. And again, this is a probability. This is an event of probability equals 1. So when x equals z, we also have that these two quantities are the same and both of them equals 1. And when x is not z, we also prove that these two quantities are the same. So now we have completed the proof that what we have is pi tilde equals times p always equals pi tilde. Okay, so this pi tilde is stationary. And now in order to get a stationary distribution, we only need to check what's the total mass of this pi tilde and normalized by its total mass. Then we will have a probability measure. So now what's the total mass? What is the total mass of pi tilde? this is the total mass. And now we switch the order of this to summation. And here we are just summing over all possible x. So it means that we can replace this, just erase this event here. And now we are summing over all n. And this is exactly the expectation of tau z plus. And from the lemma before this theorem, we show that this expectation is always finite. And since this total mass is finite, now we can normalize this measure. So define pi x equals pi theta x normalized by its total mass. Then we know that this pi is a stationary, it is a probability measure because the total mass is 1. And we also know that pi times p equals pi. So this tells us this pi is a stationary distribution. So this is the existence of stationary distribution. Is there any question? Okay, just a remark. From the construction of this stationary distribution, we can see that this pi theta we define here, it depends on the choice of z. So first, pi theta depends on the choice of z. And our pi, from the definition, we can see that for this measure pi at z, because we just showed that pi theta z equals 1. So at vertex z, we know that this pi z has this expression. So these two items are just true by our construction. And then the important remark is, after we show that there will be a unique stationary distribution, then this implies that even though the pi theta depends on the choice of z, but this pi doesn't depend on the choice of z. So after we prove after we show the uniqueness of the stationary distribution, we know that pi doesn't depend on the choice of z. And since pi doesn't depend on the choice of z, this relation holds for any vertex. So therefore, this is true for any vertex x. Yes?
You suppose the space of states is finite for all the, okay.
Yes, because when it is finite, we can normalize the total mass. So if this guy is infinite, we can't normalize it to get a probability measure. Okay, so this is the existence of stationary distribution. And from the construction, we see that in the construction, this pi theta depends on z. And pi is pi theta normalized by its total mass. And after we prove that there exists a unique stationary distribution, we know that pi doesn't depend on the choice of z. So this relation is true for any vertex x. So then, on this page, we will show the uniqueness of stationary distribution. Okay, uniqueness of the stationary distribution. First, we just recall several notations we introduced in the first lecture. So this is a matrix, transition matrix P, and this is a measure mu. And for a measure mu, we always will it as a row vector. And for f, it is a function on the state space, and then we always view it as a column vector. And for the definition of stationary measure, we know that mu is a stationary if mu times p equals mu. And the corresponding notion for function is harmonic. So f is harmonic. F is a function if p times f equals f. So here we can see this is just mu is just the kernel but multiply from the left, and f is just the kernel of p minus I but then multiply from the right. So this is the counterpart notion for the stationary distribution is harmonic function f. So now we study what happens to the harmonic function. The lemma is if transition matrix P is irreducible, then any harmonic function has to be constant. So in fact, if you still remember the results from complex analysis, in complex analysis, if you have a harmonic function defined on the space without boundary, then this harmonic function has to be constant. And this is exactly the same. So now on our state space, we don't have a boundary. So if it is harmonic everywhere, then it has to be constant. Okay, proof. Any harmonic function is constant. You can see that the idea of the proof is also the same as the proof you learned for complex analysis. So first, we suppose that this function attains max A is the maximum of this function, and x is some vertex such that okay, and fix an x such that fx attains its maximum at this vertex. And now let us check what happens to the neighbors of x. So suppose we have a vertex y such that there is a strictly positive chance to jumping from x to y within one step. And then my conclusion is the value of function at y has to be the same as the max. So why this is true? So since f is harmonic, and now we express this relation at vertex x. So we know that because f is harmonic at x, then fx equals the summation here. So maybe I should change to another notation. C, C, C. And for z, that is distinct from the vertex y. And for the vertex equals y, so I just split one quantity from the summation here. And in the first quantity here, we know that fz is less than a. So because a is the max, so this is less than plus pxy Fy. And here, if Fy is strictly less than A, then what we have is this quantity is strictly less than So here is strictly less than because this Pxy is strictly positive. So if this guy is 0, then we just have a like sign. It can't be strictly less. And since it is strictly positive, we have that it is strictly less than this guy. And now we have a contradiction because we know that this is a transition matrix. If we sum it over all second coordinates, the summation equals 1. So this equals A. So we now show that A is strictly less than A, and this is a contradiction. And this is a contradiction is because we assume Fy is strictly less than A. So this can't happen. This can't happen. So what we have is, if there is a strictly positive chance to jumping from X to Y within one step, then Fy has to be also be the max of the function. And then, for any vertex y, since our transition matrix P is irreducible, we know that there exists a sequence of state space from X at Y such that the jumping probability between two neighbors is strictly positive. And then, if we repeat the argument here, we know that if we start from fx equals a, then because p x0, x1 is strictly positive, we can derive that fx1 is also a, and we repeat the same procedure. We can conclude that fy equals a. So this shows that for any vertex y, fy equals a, and this tells us the function f is a constant. So it equals a everywhere. Okay, so this is the proof that any harmonic function has to be constant. Okay, so now we can complete the proof of the uniqueness. From the lemma, we know that the kernel of P minus I, so this is a matrix. The kernel of this matrix has dimension 1. The right kernel of this matrix has dimension 1. So of course, the right kernel. So of course, the left kernel of this same matrix has also dimension 1. And in particular, in this one-dimensional kernel space, because once we have one solution, then constant times this solution is also a solution. And in this one-dimensional space, we know that there exists a unique one such that it is a probability measure. Okay, so this is the uniqueness of stationary distribution, because we just showed that the harmonic function has to be constant, and this implies the right kernel of p minus I has dimension 1. And this implies the left kernel of p minus 1 also has one-dimensional. And in this one-dimensional kernel space, we know that there exists a unique one whose entry sums to 1. And this unique one is exactly the stationary distribution we want. So this shows the uniqueness of stationary distribution. And for this, by now we have already shown that there exists a stationary distribution, and there exists a unique one. So just to summarize on the stationary distribution is, suppose P is irreducible, then there exists a unique stationary distribution. And then moreover, we have this relation for any vertex x. So this is just what we explained before. So this is about the existence and uniqueness of stationary distribution. And now we have a break, and we restart at 10:15.